if you see the frequency spectrum here, you can see a frequency here and so many other frequencies here. So if you have here 10 frequency points, you can basically look at those 10 frequency points as zeros or 1. And if you have 10 digits, you can imagine how much information you can store in 10 digits. Because each one of those frequencies, I can turn it on and off. I can represent 0 or 1 related to each one of those frequencies. So this is how much information you can store in a chipless RFID tag. Those RFID tags can be space-filling curves like this. Can be loops like this. It can be also based on nano material, or it can be ink that's been using for tattoo and stuff like this. You can see one example here that you can have something printed on the human body that acts as a chipless RFID tag. So how does the chipless RFID tag work? If it doesn't have any integrated circuit, it's going to have transmitter and receiver antenna, and these two items are going to be resonant antenna. So those resonant antenna are responsible for receiving the signal from the RFID reader and returning the signal back to the RFID reader. The incoming signal from the reader is going to be in this form, amplitude and phase, and the return signal is going to be in this form. And you can see this represents 0, 0 here. This period here represents 1, 0, 1, and so on. So those basically corresponding to the resonant frequency of the tag itself that's basically constructed for as a chipless RFID tag. So here is an example. 3 different tags. This tag here constructed from all these resonant structure, and this represents 11151 ones here. And if you look at the frequency spectrum, that's represented by the red curve, which is here, 2, 3, 4, 5. This one here has 11001, and basically you can see at the first frequency it is active, second frequency is active, and then in the third and fourth frequency it is not active, that's why it is 0, and then again at the fifth frequency is active. So this is how we construct tags with different codes, with different bits to represent different information. The last one is only active in the first frequency, green line here, green curve, you see it here, and you can see the green curve and the last 2 bits, 1 and 1 here and here as well. All other bits are basically 0. This is the construction of an array of the same tag to give you a larger read range, but the content and the resonance of all these tags are the same. So these are basically of this type. You are going to see the 5 resonance, and all of them are going to represent 1, 1, 1, 1, and so on. Okay, so let's talk about the specifically UHF and how does it operate. And this is just basically an example. If you have a fixed reader in place and you have all these kind of items, for example, those items and any boxes like this going through a door or a hall, if you have one reader and you have all these items that are being tagged, whether the box itself is being tagged or the items inside the box are being tagged, then this reader should be able to read all of them. Now, another feature of the RFID readers is that they can read so many tags very quickly, and you can even end up with 100 tags being read per second. You need to display this information in a host media, in a computer or a screen, and you can, with this, you can, because the continuous reading of all these tags, continuous triggering and reading of them, you can see the same tag itself is being, identification of the same tag is being displayed on the screen. In a situation like this, if each bottle is tagged, and if this box has, for example, 20 bottles, most of the time this reader is not going to read all the 20 of them, maybe read 19 or 18 of them. So the accuracy of reading itself is going to range between 90% all the way to 95% most of the time for environment where we have many, many tags, especially if they are closer to each other. So these are examples of RFID readers. So this one here is basically fabricated to be installed in a hall or somewhere. these are also tags that you can install it, fix it in place. This is handheld reader. This is a very small handheld reader for a small read range. And those three images here are representing RFID development kit. You can see at the board here, you can connect 4 antennas. And that's basically this item is here on a development kit and so on. You can connect 1 antenna, 2 antenna, or 3 antenna, and you can connect it to the computer, and you can know the language that communicate with the integrated circuit in those boards and build your application. So again, another slide about active tags and passive tags. Obviously, this is an active tag. These are semi-active tags with sensors embedded into them. So I showed you the operation of chipless RFID tag. The tags with the chip is much easier. It's basically the reader is going to send the signal, then the tag is going to be, the chip of the tag is going to turn on from the off state, and then it's going to send the signal back. Many years ago, the reader was always connected to 2 antennas. One is acting as a transmitter, one is acting as a receiver. Modern RFID tags, you have only 1 antenna and basically switch between transmitting and receiving between these 2 antennas. How am I doing in time? It's okay. Okay. So one key important is basically to see the read range of any system. And we need to know what are the components that determine the read range. It's not only the tag, it's not only the reader, there are many other information, and all of them are summarized in this equation here. So if we look at this equation, frequency is a factor, and then the gain of the transmitting antenna, the gain of the receiving antenna of the reader. If the reader has only 1 antenna acting as the transmitting and receiver, then these 2 terms are going to be the same. And then we have the amount of transmitted power from the reader. And this reflection coefficient here, or this tau factor, I'm going to describe it here. But this term here represents a loss factor. And this loss factor here is polarization loss factor. As I explained to you, if we have antennas that are tags that are linear polarized and the reader is another linear polarized or circular polarization. So basically, if you have linear and circular polarization, you are going to lose 3 dB along the way and so on. This term here depends on the difference in the chip that's integrated into tag input impedance and the input impedance of the tag itself. So the mismatch at the position where we connect the 2 terminals of the chip to the 2 terminals of the tag, that mismatch is represented by this tau, and this tau is under the square root here. So all these terms are obvious and we know it. This is another term which represents the sensitivity of the measured signal that can be measured by the reader. If the reader is very sensitive, then I'm going to have very small value here. That's in the denominator here. Then this term is going to be large. If I have a sensor that reader that's not very sensitive, and the sensitivity range goes from -15 to -20 dBm. If we have -30 dBm, then we're increasing the read range as well. So the read range depends on all these parameters that are in this equation. In addition to this, the tag size represents how much power is being reflected from the tag. The tag orientation, this way or this way, also makes a difference, and the angle as well, because the tag could be like this, or it could be rotated in this direction as well. And then the multi-pass effect, if I have some objects around, it might create multi-pass for the signal going to the tag and coming from the tag going to the reader indirectly through reflections from other objects. And if you put the tag on metal objects, or you put the tag on object that has liquid, then basically, if you don't design this tag for this kind of application, then the tag is not going to function. For example, the tag, if we are having the tag as a made out of traces as if it is a dipole antenna, we know that there will be a current going through the dipole antenna. If this dipole antenna is very close to a perfect electric conductor, there will be an image in opposite direction. And the image and the dipole antenna are going to cancel each other. So basically, a tag, common tag, closer to a metal object is not going to give you any read range. But if you convert this electric tag, or this tag that's made out of traces that are basically representing electric current or electric dipole, if you convert it into a magnetic dipole and closer to a BEC, the image is going to be in the same direction. They are going to add to each other, and you are going to increase the read range. So how do we convert it from electric dipole to magnetic dipole, rather than depending on the fact that the traces are the ones that are going to radiate? We construct it in such a way that the slots are the ones responsible for radiation. That's an equivalent to a magnetic dipole. So you can see most of the tags that are working on metal objects are made out of aperture rather than traces to represent the tag itself. A small company in Finland generated this system. You can see the system. This is the outside of the system. This is basically a rectangular box. It can sit on half of this table. And inside the box, you have a rotary table here, and you have a fixed antenna at the very end. The distance between these two is no longer than 1 meter. And this chamber is basically capable of reading the information and radiation pattern of the tag inside the chamber, but using this device that's basically designed to work with this chamber. The heart of this system is the device itself, the software, and the capability of capturing all kinds of information from the tag itself. For example, we can see if the tag is working optimally at this frequency or this frequency or this frequency. And the optimal operation at different frequency depends on the optimal matching between the chip and the tag itself. And that's a key factor in designing sensors later on. This system is called tag formants, and many universities in the United States are buying this system as well. I haven't seen any system like this that's been fabricated and designed, and people are using it. Many people are using it if they are working on RFID system. Okay, so we talked about RFID tags. Before we have RFID tag, we had barcodes. So what is the difference? And now we are talking about RFID tag with no integrated circuit. So basically, one can say it is similar to barcode, but there is a big difference. In barcode, I can't read multiple barcodes more than one at a second. At every second, I can read only one. I can't read more than one each second. And each time I have to make my reader move from here to here to here, because I have to have line of sight to be able to read the barcode. I can read multiple tags simultaneously. I can read only one tag per second if it is based on barcode. I can read more than 1,000 tags per second using the reader. I don't have to be a line of sight. I can read tags scattered in the area as long as my reader antenna is covering this entire area, that I can read all those tags in this area. And that's very important to design a good antenna connected to the reader. If I need to read tags in a very wide area, then I have to have very wide beam for the antenna itself. If I really need to focus in a specific direction, then I need to design an antenna with fixed beam, narrow beam, that reads with a stronger signal in this specific direction. In terms of temperature and threshold, the tags can handle higher or lower temperature. The barcode is less tolerant. There would be some implication on the tag here. So the barcode is better than the RFID tags in this sense. The percentage of successful reads, you can see it is much higher in RFID tag. You can store information RFID tag. You can do this in the barcode. And you can integrate sensors with the RFID tag, and I'm going to show you an example. You can do this with the barcode. I didn't hear any requests for questions or any explanation here, so please, again, if you would like to ask anything, interrupt me at any time. Yeah. Okay, so I'm going to show you some of the things that we have developed specifically in terms of antenna design for readers. And this is one of the first things that's been done around 2010, 2011. A student in Finland used our partitioned loop antenna and traditional microstrip batch antenna, one antenna microstrip batch antenna for long range reading mechanism, and the loop antenna for the near field reading mechanism. So basically he built one antenna to be connected to a reader that can read small range and large range antennas tags. This is some of the new designs. You can see the antenna is basically printed on an FR4 material, and the characteristic of it, if you can notice, this is roughly about 850 all the way to 1 gigahertz. If you remember the 3 regions of the world that uses UHF RFID tags, so this antenna covers the entire range of operating frequency, and at the same time it does have a good axial ratio, about 915, which is the US band, and the gain of the antenna is reaching about 9 or 9.5 dB. The size of the antenna is not very large, but it's not small. I wouldn't categorize it as a antenna for portable reader, but definitely much smaller than commercial antennas that are connected to commercial readers. Again, simulation and measurements, you can even see that the measured pattern, which is the red curve here, predicting much wider input match and much wider operation for all those frequencies. The antenna is designed on FR4, but there is an air gap between the layer that has the patch itself and the copper plate that representing a ground plane. The circularization is being done by tapering the edges here, and the entire structure is about this size here. Okay, and this is another antenna that has 2 ports, multiple batches, but the key point here is that you can look at the pattern itself. That provides a very ultra-wide beam. If you have an area that's full of items and full of tags, then this would be a good antenna. Imagine that this antenna is basically on the ceiling here, and this room is full of items that are scattered everywhere. Then we would be able to read every item in this room in every direction. And again, the operating frequency, we were targeting about 915 or 910 megahertz. This antenna, you can see the different plane cuts. You can see how wide is the beam from minus 40 to about 40 degrees for 3 different plane cuts of the pattern itself. This is another antenna that provides mainly omnidirectional antenna. It's a planar antenna. We know that omnidirectional can get it from a dipole antenna only in this plane, but with a printed small type antenna, we can get some sort of omnidirectional antenna as well. And the size of it, you know that dipole antenna operate optimally when the length of it is lambda by 2. If you can look at the size of this antenna, 0.16 lambda, 0.16, 0.07 lambda. Much, much smaller than the wavelengths and providing an omnidirectional pattern. This antenna, even with this small size, it gives you a gain about 5 dB, which is a huge gain for a small antenna like this. There are so many people are designing omnidirectional antenna and small antenna, and they are reporting a negative gain, which I really hate to see people saying an antenna with a negative 2 dB or negative 1.5 dB. That doesn't make sense at all. Gain is basically, we should look at it as something above 0 dB, not below 0 dB. But I don't know why editors are publishing those kind of papers. If you have a negative gain, then basically you're pumping so much power into the antenna to get it even to resonate, and that's huge loss of energy consumption. Another antenna, and you can see also the entire size is a fraction of a wavelength, and this antenna also very small omnidirectional antenna. The gain is over 4 dB, and the operating frequency around 900 megahertz as well. Now, if you really would like to go to much further distance, then you can construct an array of antenna. And this kind of arrangement of each individual batch antenna with an aperture and truncated edges provide the circular polarization capability as you see it here. And you can see the the realized gain is almost 6 dB, but at this operating frequency here, let's say about 5.5 dB. I think this is for the element. When you put those 4x4, you can reach about 12 dB. So imagine jumping from one element about 4 dB to 12 dB. You can imagine this is the gain of the reader that you have transmitter and receiving in the expression under the square root. It will be 12 and 12. So this is going to increase the read range tremendously. But the main beam is not going to be wide. It's going to be narrow. And if we have an electronic behind it to make it a steering beam, then basically you can have a reader that has this kind of antenna, and you can scan the beam, very high efficient beam, very large read range. If you can afford the luxury of having electronic behind this antenna to be able to make a steering beam, and some application we need this, then we'll have a very efficient antenna connected to a reader with much larger distance of read range. Okay, so some other applications that we have done. This is the first application that we did around end of 2009 or early 2010. That was basically for the companies in Finland. Finland is famous of producing paper, and paper reels are like this, and they are huge warehouses that they are sitting and on the shelves everywhere, and they need to go into the warehouse with a reader to be able to read which reel is there and what is the identification of it. So they need something inside each one of those that are basically producing omnidirectional pattern for the tag, so we can be able to read it from every direction. So the solution that we came up with is to use a bow tie antenna. We use 3 of them, and basically in one of them we put the chip here, and then we wrapped it around the paper reel itself. And that gives you basically an omnidirectional reading. You can read the tag from any direction around the reel itself. And if you look at these are RFID tags that are made out of copper. We just made it on a copper, on a transparency sheet, and then we wrapped it around and we made the measurement. So there is no very sophistication other than the chip is already made chip, and we stick it. We had a conductive glue that basically connects the chip to the 2 terminals here. Other application, these were done also in Finland. You can see inkjet printed silver ink on a flexible material, and you can put another layer of this flexible material on top of it, and you have the tag inside, and you don't know what is inside, and it can work. You can see this similar object where the chip is connected here. This is the construction of it, and this one is made out of etched copper on a substrate. In this illustration here, these are fabricated tag. This is the commercial tag, and you can see the difference between the amount of copper area on this tag, on this tag, and this tag. The intention is this time to reduce the cost per tag from 10 cents all the way to 1 cent. You can see the traces here are basically silver ink deposited into a Kapton material, which is flexible material, and we connected the chip here, and the amount of silver ink is very, very minimal relative to the copper traces here. When you do this kind of fabrication, you can also change the read range by changing the conductivity of the silver ink by having 1 layer, 2 layer, or 3 layer, as we discussed this morning as well in the transparent antenna. That's basically information about this tag. And you can see if we have 1 layer, 2 layers, 3 layers, 4 layers, you can see the read range increases from about 5 meters all the way to about 8 meters. I sent 2 students to Finland in one summer to learn about RFID, and their project is to create an RFID tag. And they came up with this. Tampere University of Technology and University of Mississippi, they put these 2 things into one configuration here, and they put a chip here, and I got this tag to work on a plastic material, on a fabric, and etch it also on a substrate. And the radiation pattern measured here, measured in simulation, they did it basically, the radiation pattern was measured by not an automatic rotary table. They basically did it angle by angle and did it in a very primitive way. And they get very good match. One of them is undergraduate students, and the other one was a graduate student at this time. Dr. Fatma, you know him, Khalid Al-Mahgoub, who is well known in his area right now. He was a PhD student when he did this work. A challenging task is to create tags on bottles. Bottles has liquid has very high permittivity, and this was one of the designs that basically been done at that time for bottles like this. And you can see the performance here. The tag itself at this frequency on the bottle, that's the directivity for all these angles of measurement at another frequency and at a higher frequency. So those are the center frequency of the 3 different bands in the 3 different regions in the world. And you can see the directivity in the blue curve here is almost the same for reading the tag from any direction around the bottle itself. If this tag is in free space or on a planar structure, conformal or not conformal, then basically that's the directivity blue, the red and black curve. And if you put this tag on 3 bottles like this, and instead of having omnidirectionality that you can predict it from here, from all these curves here, you can see a little bit deviation because how you orient those tags and bottles, but you can still see that you can read it more or less around with a little bit of deviation. Those 3 curves represent the 3 different center frequencies for the operation of that specific tag. But obviously, if we would like to make this tag, for example, if you look at the red curve here for 866, this is the European standard, almost omnidirectional. The gain of it is basically, this is 1.5, 2 dB, so it's above 2 dB gain itself, which is still very reasonable read range. Also, you can make tags using stitches on fabric. And again, if you do this on fabric, you usually wash our clothes. If you wash it 1 time, 2 times, 3 times, and so on, you can see that the read range changes because the conductivity of the thread itself is going to change a little bit with how many times you are washing it. This is another circular Bryce tag, was designed using finite difference time domain, and measurement and verification using HFS is also conducted there. So if we talk about sensors, there are all kinds of sensors. There are temperature sensor, gas sensors, touch sensor or capacitive sensor, and crack sensor, and strain, and there is vibration sensor, and so on. So let's talk about 2 of the sensors that we have created and measure them as well, humidity sensor and temperature sensor. The idea of both of them is basically to change the substrate material properties. basically changing the permittivity of the substrate material of this antenna, of this tag. If I change the permittivity,